Four or three? Feel like we only have three. We have chapter 3, chapter 10, and chapter 11. Yeah. Okay. All right, so natural logarithms have a different base than anything else. That's what makes them exciting and fun. So natural logs have a base number e. So you know how like a common log, we don't write it, and it has a base 10, and everybody knows it's a base 10? So natural logs have a base e. So e is named after the Swiss mathematician Leonhard Euler, and it is another irrational number. It's another irrational number like pi. It doesn't repeat, it doesn't terminate, and this is the approximate estimate of e. Now you should have an e button on your calculator, I think. Yes, I do anyway. So you guys should have a natural log button. So you're looking for a natural log button is the ln button. And then above it or close to it should be the e to the exponent x. Okay? So natural log is a different beast altogether, so it has to be a different button on your calculator, because if you hit the log button, that's a common log that has a base 10. So the ln is your natural log button, and it has the to the exponent ex. So here's the thing you guys need to know, is you need to know the approximate value of e.
What?
2.72. Just like you guys know pi is 3.14. 14. You just need to know the approximate value of e.
Why is that the way that you're just like, who decided that
Euler, he discovered it. There's a relationship between it. I'm not 100% sure what it is. Don't want to make up a story, but I could make up a good story. Okay, we got to keep trucking along because this is it's a little bit longer of a lesson. So you can write it as log base e if you want to, but that's the same thing as the natural log. So if you see the ln, that has a known base of e. And so then I just so if you're looking between this and this, I took it out of log form and put it into exponential form. I feel like I went a little too far. A little too far. Okay, so we found E on our calculator. So using that, I want you to use your E button for the first time. So on mine, it's a second function button. So I have to do second function and then the natural log, and it brings up the letter E, and I'm going to put in 3.2. Pardon? Got it? 24.5325. I just want you guys to get comfortable using this button on your calculator and knowing how it works. So in my other calculator, this one here, again, it's the shift button. So shift, and then this, and then 3.2. Mine automatically opens up the brackets. Everybody good with that? Okay, so now you're going to use your natural log button. And if I'm not rounding, ladies and gentlemen, you guys know you can use the ellipses. The ellipses to say that it continues on forever. Yeah, you guys know that? Of course you do. Okay, now you're just going to use your natural log button. So ln of 0.0051. So you should get a negative 5.2785, and I'm just going to use my ellipsis. So I'm not rounding, I'm just saying it continues on forever. When you use the ellipses, you don't round, you truncate. Truncate means just to cut off. Okay. All right, we ready? And you guys know this, right? You guys know that a log, when it has the same base and same argument, it evaluates to 1. It's a handy trick, like you can always calculate it for sure, but it's just a handy trick to save you time. Like you don't have to show your work for that one. That's kind of like a mathematical known truth. You can just put 1 instead of that. So instead of using the log to solve exponential equations, you can use the natural log button and you'll get the same answer. Usually ln is used when solving equations that have e because eln is equal to 1. We just talked about that because the base on the natural log function is an e, so your argument would be e, and that would have a value of 1. So it's the same principle here as it is here. Okay, are we good with that? So natural logs, ln's. Okay, we're going to see how fast we can graph this first one. What do I control? What do I control? What am I going to substitute in? Would it help to change this to exponential form? Okay, change it to exponential form. What's my base? 10. My base is 10. What's my exponent? Y. And that's equal to x. So which values am I picking? My x's or my y's? Y's. Where's the asymptote? Where's the asymptotic behavior? X equals 0. Yeah. So it's going to be that y-axis again, right? We're going to have the asymptotic behavior. On any logarithm graph, you're going to have a vertical asymptote. But you all know that. Is the pink, can you guys see the pink okay? Okay. I don't know what the easiest one to do is here. Twos. Are you okay with that? Is that what you meant, Basil? Okay. Oof. All right, so my common point is 1, 0. I'm at 10 and 1. And at 1/100th, I'm like really, really close to the line. And here I'm really close to the line. So I've got that going on there. Everybody's good with that, though. You guys could graph a basic log function, no problem at all. This one's just a little bit more difficult because it's got a bigger base on it. Okay, so are you guys good if I slide up or? Nobody's screaming. I like it. So looking at that first one, all right. I said this is the logarithmic graph. Because if we put this into exponential form, we can put it in exponential form, but it's a logarithmic graph. So we anticipate we're going to have asymptotic behavior on the y-axis, right? Like, this is what's important about this. We know its common point is going to be 1 and 0. So if we were to put this in exponential form, what would it be? What's the base on ln? E. What's the exponent? Y. And that's equal to x. So the big difference between this one and this one is that this exponent is x, so that makes it exponential, and this one, the exponent is y, which makes it logarithmic. Okay? This is exponential form of a logarithmic equation. So what do we pick in this one? We pick our y values. I'm going to get lazy. I'm going to pick those. So if y is 0, what's x? 1. If y is 1, 2.72. And if it's at negative 1? Oh, you didn't like that? There's decimals inside of fractions, and it's bad, oh bad. 0.37. That's better. And you could have estimated that, because what's 2.7? It's close to 3, 1/3, 0.3 repeating.
So true, this guy. Yes, absolutely. I could have guessed that.
Well, because I may make you graph this on a non-calculator portion.
And I would give up. Okay.
And you will give up? Oh dear. So our common point, if we do these again, I don't need to do these again. I can do 1, 2, 3, 4, 5. Oh, geez, Louise, you can't even see my graph. Jeez, Louise. All right, so I'm going to plot my points. Common point. That's exciting. At a third, I am at -1. And at approximately 3, I'm at +1. So we have that asymptotic behavior happening again. So you're going to be, if you're not going to draw in your asymptotes, you're going to have to be very, very careful of where you put your points and your function line. Function curve. Okay, exponential. What are we going to do with this table of values? Flip it. It's a very good possibility that you guys will have this, graph one of these with transformations on your test or on your exam. Okay, where do we anticipate our asymptotic behavior to be if it's on an exponential graph? Yeah? So that would be my x-axis, right? Exponential graphs are going to have that asymptote at y = 0 along the x-axis. Yeah, so, and our common point changes. Our common point is now here. Ooh, I didn't put any increments on. So at -1, I'm at about a third, And at positive 1, I'm approximately 3. So shouldn't be too off the mark for you guys. Like, this is pretty standard of exponential and logarithm graphs. Now we're dealing with just a very specific value of e. How do you feel about that? Not too terrible, maybe, possibly. It's fine. It's fine. Am I good to flip? All right, cool features. Cool features of natural log graphs. Okay, super cool. All the rules that you learned in 8.3, all the log laws apply to natural logs because they are still logarithms. Any transformations in 8.2, you can still apply to natural logs. And like all the asymptotes and everything like that, they still work any way the other base is. Okay, so remember how we did the equality thing 8.4? Was it in 8.4 we did it? Where we just dropped the logs and equaled the arguments? Remember when we did that? Same sort of principles in here. Okay, so let's look at this first one. So this is fun principle number 1 in the yellow. Okay? This is fun principle number 1 in the yellow. Let's apply our log power law. It's where we can't have an exponent on the argument. What do we do with it? We bring it to the front. So this would be x equals L N E. What's the base? Oh, that's terrible to see. Sorry. X, L, N, E. What's the base on the Ln? E. So what do we know that this evaluates to? 1. Isn't that exciting? Yes, the E is the base here. Because we know that any natural log has a base of E.
So E is both the base and the argument?
Anytime you have the same base and argument, it evaluates to 1. Whether it's an E or whether it's a 5, base 5, anytime the argument and the base are the same, they evaluate to 1.
But why is that unique to E?
It's not.
It's unique to the LN.
I thought it was cool features of natural logs and stuff.
Okay, well, it's cool features of logs, sorry. Okay, this one. It is also equal to, okay, I have an exponent on one side, I want to solve it. This is 8.4. What do I do to both sides? What do I do to both sides? I log them. 8.4, you log them. So, but because it's a base E, do I just log them or do I natural log them? You natural log them. So you're going to have Is everybody with me so far here? So all I did was log both sides of this one. I'm on the middle one now. What? Well, I can't undo it now. Okay? You guys see it all on your page, so I'm on the middle one. Guys, I'm just proving these to you. I don't have to as long as you guys are comfortable with that these are known truths. Okay, well then, in 8.4, we learned when we had exponential form, we were trying to solve something in the exponent. step 1 was to log both sides. But in this case, we have a base of e, so we're not going to just log, we're going to natural log, right? So now we're going to apply the power rule on this side. So this is going to be ln x times ln e equals ln x. You with me so far here, folks? What does this equal? That equals 1, so we have ln x equals ln x. And when they both have the same base, what can we do? We can just drop the logs. So then it would be x equals x, or like you said, Nicole, this is a true statement. She did say that. Nicole's all over it. She knows what's going on. And then this last one, I'm going to highlight it in green, which is probably not going to be a good idea. No, not a great idea. Do you guys know why this is true, right? We've done this one like 3 times already just in this lesson. Because it's the base. It's ln base e to the argument e is always going to equal 1. And that's true whether it's a regular log or not. All right. Okay, you're going to apply your log laws from 8.3 to some natural logs. You can do it. Okay, let's go. They start on the 15th and go to the 21st. So we'll start on a Wednesday and will be the last exam on the 21st. Okay, so when the arguments are multiplied, what do we do when we expand it? Add. And when we divide it, subtract. And remember that we can only do these laws when they all have the same base. What is the base of a natural log? E. I'm just saying it out loud. Now we're going to apply the power rule to this because we can't have exponents in our arguments. But it's not. If you slow down and think about it, it's the exact same rules we did in 8.3.
All math is completely made up. Like, wow.
What?
All math is just completely made up.
Okay, we're going to solve. We're going to solve for x for this next one. Okay, so what's we going to do? Wait for me to do it. I love when we wait for me to do it. It's probably my favorite thing.
Use our log laws.
We could use our log laws for sure.
But I'm guessing there's another way to do it.
Nope, we're going to use our log laws. We're going to use 8.4. So it's a little bit of log laws and it's a little bit of strategy. Step 1, when we're solving for an exponent, what do? Log both sides. But what kind of log am I going to use? A natural log because of this e, but you have to use the same type of log on both sides. So we're going to have ln e to the exponent x. This one we're going to solve. Are we good? Can I keep going? So now we're going to apply the power rule. What does the power rule state? You take the exponent and you pull them out front. So this is going to be x ln e and then x plus 1 ln 2. Okay? Now we're going to distribute the log through the exponent.
Can we change the ln to a 1?
Oh, you want to do that right away? You're wild. Crazy.
Don't skip it. It's fine.
It's not skipping steps.
Ooh. Poor Basil, just wanting to be efficient, and that is a solid no-go.
I just can't handle my gigantic brain. Too much.
Okay, so what do we do from here? We bring all the x's, any log with an x, bring it to one side, and any log without an x, like just numbers, goes to the other side. So this has to come to this side. So we're going to have x ln e minus x ln 2 equals ln 2. What's the next step? Common factor out that x. That's not good. It's not. Oh, but you weren't here, so that's good that you're guessing. Good job, Nicole. Oh, then that's not good. You were here, Danica. Okay, I want to get x by itself.
Divide both sides by that.
Okay, so Basil wanted to change this to 1, and he totally could have at any point. So now you're going to do this side, in your calculator. So x is equal to ln 2 divided by ln e minus ln 2. So those are arguments. I've got no bases stated anywhere on here because they're all base e. And you've got to use brackets in your calculator.
Where is the button for e on your
It's
I don't need it. But
natural log. Natural.
look for the button for e.
You always have to put it to the exponent. Like, so you would do, if you just want e, you'd have to do e to the exponent 1.
So it's going to turn into a 1 is what you're saying.
I don't know what you're saying.
When people are typing,
Okay, where's your natural log button? Do you see it? So in my calculator, I can do it all in one step. So ln 2, I'm going to close my brackets, divide by, and then I got to open up my denominator bracket. You can't. Well, you can. I mean, you can put in e in exponent 1, but you need to know that ln e has a value of 1. No, I will always make you do something like that.
see, this is why we should just do my trick and just change to a 1 already.
Because what's e to the exponent 1? Itself, right? Oh, I missed a bracket. Hang on. So, really, ladies and gentlemen, the easiest thing to do would be to replace this ln e to the exponent 1. It's always 1. Ln e squared? Like ln e squared? So, I'm confused. You're pretty passionate about it, but yet I don't know how to answer the question I don't know. I don't think that was very kind. Okay, so again, this is 8.4 in a nutshell what we did here. This is what we did in a nutshell in 8.4. So, log both sides. Good times. Okay. So this becomes a lot less complicated if you go back to these three rules here, or these three laws of equity here. So e to the exponent ln argument of some value of x, you can just drop this and bring the x down. So when I look at, flipping the wrong page somewhere else. So when I look at this, if it's e to the exponent ln with some argument, that is simply equal to so using the laws of equity make this so much easier to do. Well, I did prove it to you back here. We proved how we did this in this situation here. It's a mathematical known truth, so you don't have to prove it every time. Like, you can do the math, you can follow all the steps where you log both sides, and I can show you how to do that. But there is a law of equity that will make it a lot faster.
You have the most complicated thing in the world.
You can just bring it down. As long as it's e to the exponent ln, your argument just gets brought down. Do you want to do it the long way so you can see? No? Nobody's signing up for that? No. Perfect. Okay. You'll trust. I like it. Okay. So the next one, we're going to solve for x. No, but good strategy, but why can't I drop the ln? Because this one has no log. This one has no log, so I can't just go ahead and drop the logs. Yep.
That's like a law where you can drop all the logs to a left and
Yep. Yep. As long as you have a single log on the left and right hand side. So what I'm going to do here is I'm going to make it into a single logarithmic function. Just one log. Because then I can put it into exponential form. So I know I can't use the drop logs because this one doesn't have a log. So my next strategy is to make it into a single log. So I'm going to have ln plus 1 minus ln x equals 1. Because then how can I write that as a single log? I'm going to use my log laws, right? Because they have the same base. So ln and my argument will be x plus 1 over x. Oh, that's not an L, that's a 1. Nope, you don't do that. A kitten will die. I know you didn't mean to say that. Okay, where do we go from here? When you have a single log, the strategy you're going to use is to put it in exponential form. So when you have a single log, you're going to put it in exponential form. No, we need to solve for x.
Do we change it?
What do you want to do?
Do we change it decimal form already, or should we do it at the end?
I would do it at the end, but I think people might struggle to see that. So,
are ln and e the same thing?
no. ln, just like your common logs, have a base of 10. All natural logs have a base of e. I took the base from that log. So natural logs have a base of e, just like common logs have a base of 10. Is the natural log, is the symbol we use for natural log. Okay, so I'm going to use, like, e is that irrational number, so I'm going to wait till the very end to do anything with it. So I want to get x off the bottom. So I'm going to times both sides by x. All I did was times both sides by x. You guys have done this a lot. E is just a number. Would it help you to see it as just a number? Now what do I do?
Bring the x to the other side. And then
Brilliant.
Factor it out.
Can't I just combine like terms at this point?
Oh, you can't do that. Sorry, I didn't.
Yeah, no, and you would have had to common factor it if you were doing E until the end. And that's a more accurate way to do it. What's the coefficient on that? Guys, if it was 3x minus x, you'd have no problem getting 2x as an answer. You throw some decimals in there and it's game over. When I'm done dividing, yeah. Is that what you got, Basil, when you common factored it?
0.581,976.
Okay.
The first derivative. I did it.
Okay, so ladies and gentlemen, that ends the natural log portion of this lesson. Portion. We have two other things to accomplish. Well, yes and no. Okay, so we had this discussion before. Yeah. It's just plugged into the wall back here. You can't take it. You've got to plug it in. I was like, put it on Do Not Disturb. Aw, thanks. Okay, so lots of applications of exponential functions. We talked about this before briefly, is that like on the final exam or on the test, I might give you a formula that you maybe haven't worked with before and you need to solve for an exponent. So you might not have seen it before, but all the strategies will be the exact same. So that's why I'm showing you some popular formulas that come out. We've done the Richter scale. We've done that as an example. We've done the decibel scale as an example. There's an X-ray absorption one that is a log function. This is continuous compound interest. That's basic compound interest. These are things that we do in essentials, but we never solve for the exponent. That's what like we solve for, like the annuity. It will tell you what all of these things are equal to. And you guys have done exponential growth and exponential decay. No big deal. With a base of E, you're going to apply natural logs instead of regular logs. That's really the only difference. So just know that you may get something. I want to say one of the exam reviews I gave you, one of the questions right off the hop is this one here. And you got to solve for an unknown exponent. So that's fun. All right, so let's do some exponential growth and decay here. Okay, here we go. In 1960, Smallville's population was 1,200, and in the year 2000, the population was 2,000. Determine the population for the year 2050. And so I give you a hint, and I will tell you that this will be a question on your test. Not this one in... You say this every time. You say this every time. And the answer is no. This will not be the exact. But it will be a similar question.
So the same question about the numbers?
No, a similar question. I love you guys. Okay, so we are going to use, and do you guys notice that these are the exact same formula? Just the letters are a little bit different. What does A initial usually stand for? The initial, the beginning, right? So this one's a little bit more, that makes a little bit more sense to me, but P equals the population, like so. Both examples are exactly the same formula, just written in a little bit of a different way. Okay. So we're going to say P is the population. And we're going to say that this one is the initial. Too bad I can't spell initial. Okay, so we've got some information here, and we need to solve for the coefficient K, is what we're trying to solve for. So we know that the population is 2,000. The initial population would be 1,200. We know E is just a number. We're trying to solve for K, and what is T? How much time has passed? 40. Yeah, that's the E. So you guys have done this before. This is just solving a logarithm. There is nothing different about this than the 8.4 lesson. There's nothing different. So we want to get that exponent by itself first, right? We want to isolate the power. Divide by, get rid of that 1,200 in front of it. Okay. So, step one, when solving for an exponent, what do we do to both sides? Log both sides, but in this case we have a base of E, so we have to ln both sides. Okay, so now we're going to use the power law in logs and move that exponent out front. What do we know ln has a value of? 1. So we know that ln 1.6 is equal to 40k. I don't want 40k, what do I want? Just k, so I'm going to divide out the 40. Yep. Okay, so here's the thing, ladies and gentlemen. This is not the, and it's 1.6 repeating. I need to go back and do that in my calculator better. Okay, yep, but we need to use all the decimal places. So I'm going to put my K on the other side, just so.
Whoa, I didn't get that many. I got 0.012770.
We probably didn't use as many sixes.
I used the fraction version.
Oh, you used the fraction version?
Yeah.
Okay. So we're all approximately at the same place. We have not answered the question though yet. Right? So all we had to do was find the coefficient K first. So now we're going to actually answer the question, which is what is the population in the year 2050? So now, So now my formula changes to P equals AE. What do I know K is? 0.01270640058, or use the one that you did, times by T. You don't have to do anything. It really depends on which one you want to use. You could use the 1200 population, then your T would be different. I'm going to use the 2000 population because I can do that math in my head of the time. So Basil had asked, does it matter which population I use as my initial? And the answer is no. I'm going to use the 2000 population just because between the year 2000 and the year 2050 is a nice number of 50. I mean, if you use the 1200 population, what would your T be? It'd be 90, right? So we all should get the same answer. So we're trying to solve for population. My initial population was 2000. E to the exponent 0.127064058, and my T is 50 years. Oh, sorry.
It doesn't matter.
Because I used this information as my initial population when solving. You could use the 1200, but your T would be 90 then. Right? So it should work the same. So I just times those two numbers together. Order of operations says I'm going to deal with my exponents first, so I'm going to deal with that first. You okay?
Oh, now we're doing operations.
Because I evaluated it. I did e to the exponent of that. We're dealing with people, so should I have decimals? No, that doesn't seem polite nor nice. Okay, so hint, hint, nudge, nudge. There'll be a question on the test like this. And I will put the hint to solve for K. Just go. Just go. Don't take them with you. Don't take the whole pad with you. All right. 3787. It's up there. You got 377 who? Okay. Okay, I'm waiting. No. No. Yep.
I get 1.88, like 76.
Did you use the same decimal as me?
Yeah, I'll put it from the 9 to.
Okay, let me try again. 63853. Okay. Okay. Radioactive substance is decaying. And we know it's a decay because it has a negative exponent on there. Guys, exponents are tiny. Make sure you pay attention to the positive and negatives on them. All right, so how much is left after 3 years? Super easy. So it's telling you what A is, and we're just evaluating. So you know A, and you know T. So Y is equal to A, which is 80, times by E to the exponent negative 0.2 times 3. And I just do some brackets around there to help remind me in what order I should be doing stuff. Okay.
It's not funny. I don't know why it's funny.
So, straightforward, I'm going to put that into my calculator. Don't forget your negative button. Oh. That's it. So it's a nice, easy plug and chug one. The next question takes a little bit of thinking. So the half-life of a substance.
It's the amount of time that it takes for something to like half of it to decay.
To decay to half of its original amount. So if we know the initial amount is 80, what's my Y value? 40. And so what we're trying to find is the time it takes for that to happen. So you might get a question like this. So you need to know a little bit about what a half-life is. And so it's the time it takes for the original amount to decay to half. So if you were given no information, could I have used 1 and half? For sure. Could you have used 10 and 5? Yes, you could have used 150. It doesn't matter. For a substance to decrease to half of its original mass. My Y for the first one was 40? Right, well, it's close to 40 for sure, yeah. So they are two different questions. So we know we're going to be around the 3-year mark, but we're going to get more specific. So okay, so now this is the 8.4 again. This is lesson 8.4 because we need to solve for an unknown exponent. Mm-hmm. And what kind of log are you doing? Natural, because we have an E. And I'm going to skip a step, and I'm going to do my power law while I'm here as well. I skipped the power. Yep. Are you okay, Basil? I thought somebody just threw something. Okay.
Okay. We're just gonna be grateful that we're gonna be grateful that for the last 10 years you could have grateful for those and stuff. And then for best class. That was pretty bad. No. It's the fun experience.
So this is kind of like the application of the 8.4 part of it. No, we have one more thing to do. So that's the second portion of a 3-portion lesson. The last one is just using your calculator for good things. Okay, so if you find yourself in a place where you have your calculator and you need to evaluate a log that doesn't have a base 10, I mean, this is rarely going to happen in your world, but I just want you guys to know this. So if you have log base 2, 3, you can actually put it into your calculator as that.
So the argument is.
So it's going to be the log of the argument divided by the log of the base, which turns into the argument.
So could you technically do that for everything?
Yep.
If you had your calculator?
If you had your calculators, but you won't.
You know my calculator has button on it, just use log and throw base on it.
Oh, you can put a base on it?
Yeah.
That's nice.
Yeah.
Yeah, mine you can. Okay, so if I were to put this into the calculator, I would do log 17 divided by log argument 2. And so both of them would have base 10s. So that's the way you can do it in your calculator. So that's the last portion of today's lesson. That's it. That's all. So, yeah.